welcome back to KhemWithKess. Today on addition reactions of alkenes, we're talking about oxymercuration-demercuration. All right, that word is extremely long. See, I can't even speak right. Let's go ahead and break it down. What is this reaction doing? It is going to add water. So this would fall underneath the hydration category. So I'm expecting all of this that's on the line that you will memorize will be the reagent that we're using, but ultimately we are just adding water to this picture. So let me just leave that for you. So I like to draw water like this purposely. Now, oxymercuration also is, let's see, how would I say this? This one follows Mark's rule. Mark's rule says that we prefer it to be more stable always. So when I pretend as if the double bond is not where it lies currently, you would tell me the first carbon is tertiary and the second one is secondary. So this reaction, I'll go through a mechanism at a later time. The Hg, when you see that, let it be your indication for more stable. And when you're looking at your group, the hydrogen would always go to the least stable, but the OH group is the one that we're focusing on that would go to the more stable location, giving you the answer choice of this. Now, also, at some point in time, the mechanism really does follow the bear hug routine. Now, I mentioned bear hug in halogenation's video, so if you haven't seen that, go take a look at that for me. So when you add the actual OH onto there, this reaction would fall under anti-addition, which means if we have to show any type of stereochemistry, it would be trans. So I would expect to still get this OH here, and the hydrogen would go to the opposite end, but you would need to show actual stereochemistry for the addition in case the instructor wants to see that. So just again, drawing both versions for you. Now, the bottom portion. Now, what if we're given a double bond that both carbons are symmetrical? Meaning, well, technically, are they really? I guess I kind of led ahead with my question, but because both of the carbons are secondary, now it's about looking at the problem in totality. When I look at this side, I notice I have a total of 1, 2, 3, 4 carbons on this side, versus on this side, I only have 2. So since this molecule was unsymmetrical, and I could clearly distinct which side is more stable, I would expect oxymercuration to add to the more stable carbon, giving us our answer of the OH adding to this carbon. So even though something can both be the same classification as carbon, like primary, those are a little bit stranger pictures, but both of them being secondary, you can distinguish what to do. And again, if the problem asks for stereochemistry, please make sure you provide it.